Welcome to the next edition of Chatting with Chuck. I'm your host, Chuck. Today I'm going to talk a little bit about the IIoT, the Industrial Internet of Things, as you may or may not be aware, and talk a little bit about hard edge gateways. And so bear with me as I took some notes and wrote down some information I thought was interesting, and let's just jump right into it. There is clear evidence that the IIoT, which is the Industrial Internet of Things, is rapidly expanding its reach. For instance, the number of devices connecting to the internet is growing at 15 to 20% a year, and the total of connected objects is expected to reach 25 billion by the year 2020. IoT data management demands will increase by about 19.3% through the year 2022. There are several reasons for the advance of the IIoT. One is that the cost of connecting a device has fallen, thanks in part to the continuing drop in price for semiconductor technology. Another driver for the growth of the IoT is that a benefit of communication is an increase in available data. That means that manufacturing floors have access to sensor and other data that machines generate. In turn, this allows better decision making about the health of a machine and a process. There can be, for example, big data analytics of a factory, which raises the possibility of tuning production to skew to a higher end output with a result of lower failure rate. Connectivity also enables two-way communication with remote access, monitoring, and control manufacturing devices and systems. This could then move a factory from reactive repair method of operation to one of proactive maintenance, resulting in less unplanned downtime, greater productivity, and lower cost. Those benefits, however, run into a stumbling block. According to IMS research, about 85% of devices in use currently are legacy systems and often run standalone, isolated application. Industrial systems tend to have long lifespans, with many in use for decades. Thus, many of these legacy systems lack any connection capability, have some sort of proprietary one, or are otherwise unable to link up with the modern IoT. In the industrial Internet of Things, communication is typically built on Ethernet and web-derived technologies like HTML5. To overcome this legacy device barrier, deploy an IoT gateway. This will serve as a bridge between legacy devices and the wider world of systems, the cloud, and the Internet of Things. However, be sure to select one with the right physical and communication characteristics. Let's talk about the legacy challenge. However, before getting into the parameters of an IoT gateway, first let us look at the nature of legacy systems. Consumer goods have life expectancy that ranges from about 10 or so years for major appliances and systems down to as little as perhaps 12 to 18 months for a mobile technology. Thus, new technology and related standards tend to move through consumer goods relatively short order. One reason why some companies are turning to bring your own device, or BYOD. This leverages the latest technology which workers already possess without requiring an IT procurement, deployment, or support cycle. Industrial equipment, in contrast, tends to have much longer life cycles. For instance, according to the American Society of Heating, Refrigerating, and Air Conditioning Engineers, the life expectancy of heating, ventilation, and air conditioning equipment is roughly 15 to 35 years. A similar difference is found in the information processing space. Processors for consumer products may have a production lifespan of 5 or so years. However, processors for industrial systems from major manufacturers have much longer production runs, and industrial board makers take pains to keep engineering changes to a minimum. This reduces the high cost of design changes, costly maintenance, and upgrade efforts. There are good reasons to take this approach. Industrial systems are subject to greater temperature changes, more vibration, increased dust, and other environmental extremes than in the case of consumer applications. Thus, industrial equipment and IT require special qualification and careful design to function. What's more, these control and automation systems must often carry out tasks in a manner that can be certified to be safe. Once the certification is obtained, there is even more reason not to make changes. Finally, for many applications that are only concerned about machine control, a simpler and less powerful processor may be more than enough, as proven by still widespread use of 8 to 16-bit controllers in industrial applications. What this means in the context of the IoT is that many legacy systems were designed a decade or more ago. While the IoT was certainly a possibility then, the basics of connectivity, protocols, and programming languages were still being worked out. Industrial system designers frequently opt not to include, any communication capabilities. Doing so simplified the design, saving money and increasing security. After all, a system that is not connected cannot be hacked or otherwise compromised by an outsider. Those designs and applications that did include a communication capability had to settle on one of several competing approaches that were popular years ago. The choice may be right or wrong in light of the evolution of technology, but whatever the selection was, it constrained the communication channel and capabilities available to the system for the life of use in the application. Still, linking these legacy systems to the IoT, it's easy to say, would bring substantial benefits. One is that would break the barriers that separate operational and information technologies. If the connection is done correctly, one result would be the distance between the automation and the control systems on one hand, analytic package on the other would be erased. Data could then flow from the factory floor, be analyzed, and appropriate actions and adjustments to manufacturing made. There also could be remote access and monitoring systems in a plant, leading not only to better control but also better maintenance. Let's bridge the gap here. An IoT gateway can overcome legacy challenge by linking systems on the factory floor with the IoT to the cloud. In effect, it supplies the missing communication capability. What's more, since it's a single and separate add-on unit, it can be upgraded and changed out as need be. It's also possible to install such a solution in stages, deploying it first to those systems that provide the greatest return of investment, and then rolling it out to others when doing so makes the most sense. An IoT gateway, like any communication solution, must be cost-effective. To see why, consider that it will be applied to legacy systems, so it may be going into situations where the other equipment is substantially or fully depreciated. That helps the bottom line of a manufacturing process, but also places constraints on any upgrade or add-on. After all, many additions to the existing system would have a significant impact on the bottom line and profitability. That makes it imperative that the IoT gateway be cost-effective. In addition, a gateway must offer a wide and comprehensive support protocol. As an add-on, a gateway will have to successfully interface with a variety of PLCs and other devices, which may communicate with different interfaces and protocols. The gateway must be able to deal with all these. The gateway should also handle data acquisition and protocol conversion of the data into an appropriate format. There is, on one hand, a benefit to increasing computing power that is the edge of the network. Particularly, it can be done without changing the entire structure and architecture of a system or machine. A gateway need not, on the other hand, necessarily offer extensive computing capabilities. This is because heavy-duty analysis can best be done elsewhere, such as in the cloud, where compute power can be added on as ad hoc basis. An industrial PC can meet these IoT gateway requirements and satisfy several other important parameters. Critically, an IPC can be both rugged and compact. The first is a necessity because the application is an industrial one, and so any device will be exposed to temperature, humidity, vibration, and dust extremes. An IPC is designed to work in reality in such conditions. As for the requirement that a solution can be compact, that arises because any gateway will be an add-on to a legacy system. The amount of available space may be very limited, which means that a communication solution should take up as little volume as possible. A related point is that a gateway must be modular, given that it can need to fit into a small space. It may be necessary for a solution to be tailored so that it offers only the bare minimum of functionality. That is easier to do if a gateway has a flexible form factor and configuration is possible. Finally, an IoT gateway must provide web and cloud access, as well as offering support for an HMI. The first option is important for any remote access, such as when connectivity from a distance is desired. The second is extremely useful when changes are going to be made locally. Again, a solution based on an IPC can offer these capabilities. What about the benefits? Well, when installed, an IoT gateway makes it possible to acquire, store, filter, and analyze the data generated daily by systems on a factory floor. Such information can prove extremely valuable. Consider, for example, a laser that welds two pieces together. Each machine could tally up how many parts are processed in an hour or a day, how long the operation takes, and various other bits of information, such as sensor reading as to how successful the material processing is. The data can be combined with other inputs from machines or systems. These can be either in a production process. They also can come in later process, such as final quality control sensor or an associated QC check. This information can go through analysis, allowing for instant and spotting of trends. One machine may consistently output product that has a greater likelihood of being in spec and lower chance of being rejected. A second may do the opposite. Big data analytics can reveal such trends, particularly those that involve interaction between machines or conditions that only arise in specific machine processing. The insights possible with this type of volume and data include determining which machine or set of machines make the best product and offer the highest productivity. Such information, in turn, can lead to a better and more streamlined process, thereby increasing throughput, reducing costs, improving quality, and even cutting energy consumption. Beyond that, more data can improve machine maintenance. For example, linking information on the status of a system with the quality of its output and analyzing this data can cover patterns that can be used to predict machine health, even if there is not active machine health monitoring going on. These patterns or associated data could then lead to proactive maintenance, allowing machines to move from a reactive stance in which problems are fixed and then happen to be one in which issues are resolved before a machine goes down and product is possibly ruined. There are many benefits to a proactive approach. Maintenance can, for one thing, be scheduled in advance, and those times when the output is minimized. It also could turn out that the maintenance can be reduced thanks to only fixing machines when there is a need and not according to some rigid schedule. Finally, the chance that production will be out of spec and therefore either reworked or scrapped can be lessened. Together with this less unplanned downtime, these benefits can yield a payback. So in conclusion, as I pointed out earlier, the IoT, the industrial internet thing, is growing rapidly, but there is a significant barrier: the number of legacy systems that lack the required connectivity. Since these devices still function and represent an investment, they're going to be discarded. Or I should say they're not going to be discarded. Therefore, to realize the full benefits of the IoT, a way to bring these systems into it must be implemented. That can be done with an IoT gateway. It must, however, be cost-effective, support a wide variety of connection protocols and standards, and provide for remote access, as well as being rugged and compact. An ultra-small industrial PC has the required form factor and can often meet these capabilities. Deploying such a system, particularly if it is modular, can be rolled out in stages. It can be an efficient way to implement the IoT. The benefits of doing this could include acquisition, storage, filtering of data. This information can increase throughput, reduce costs, and improve quality, thereby helping realize all that the IoT has to offer. Well, that was just a few minutes there on why smart edge gateways for IoT applications are good, especially in legacy systems. I hope this provided a little bit of a help to you, maybe at least some interesting material to take a look at. This has been Chuck, and once again, this is Chatting with Chuck. Please stay tuned for further episodes.